record. I share my screen. And we begin. All right, so again, today's last lecture, and in fact, we may not even take the whole time today. We're just going to see how things turn out here. All right, and so last time we were talking about phase transitions. Okay, and what we showed was that phase transitions in general are a consequence of mathematically pathological behavior in the free energy and its derivatives. All right, so we get pathological behavior in free energy or derivatives. Okay, so for example, our first example of this was the ice to water or water to steam transition. And so what we saw there was that this is characterized by, if you look at the energy of the substance as a function of its temperature, that this transition from one phase to another in water is characterized by a discontinuity. All right, so for example, you start out here, and as you, with ice, okay, at some initial temperature T naught and some initial energy E naught, and as you add heat energy to this thing, its energy increases linearly with the temperature. Eventually you hit the melting temperature, which is some critical temperature, and what happens is that the energy jumps, right? So you keep adding heat energy to the material. Where that heat energy goes is in breaking the bonds that hold the material together, as opposed to heating it up. And so you get an increase in energy without a corresponding increase in temperature. So you get a discontinuity here whose the magnitude of this discontinuity is proportional to the latent heat of the transition. So going from ice to water, that's the latent heat of fusion. Going from water to steam, that's the latent heat of vaporization, so on and so forth. And then once you make this transition, then it starts increasing again. Okay, so now as we've shown previously, the energy is the expectation value of the Hamiltonian, which is related to the first derivative of the logarithm of the partition function. In other words, this is at least proportional to the free energy. And so what happens, so in other words, the energy is the first order derivative of the free energy. Okay, I thought I do have it on do not disturb. All right, I don't know what the hell's going on. Anyway, it's the last one anyway, so let's just roll with it, shall we? All right, so this phase transition is characterized by a discontinuity in the first order derivative of the free energy, and hence this is what's described as a first order phase transition. Okay, and so in general, first order phase transitions are characterized by the existence of a latent heat. All right, so when all a latent heat means is that you put energy into the system without changing the temperature. Okay. All right, so these are characterized by a latent heat. All right, the other example we talked about was the example we've been talking about for a week or two now, and that is magnetization. Okay, so the magnetization, well, so first of all, before we do that, because we get this discontinuity in the energy, and the energy is related to the first derivative of the free energy, that is the slope of the free energy. What this means is that if you look at the free energy, God, What the hell? Okay, I don't know what. Okay, I don't know what the hell that is. Making my life difficult here. Fine. Okay, so if you look at the free energy as a function of temperature, what this discontinuity in the energy means is that in this function somewhere there is a kink. Okay, so in other words, there is a point where the derivative is not defined because you get different values for it coming from different directions. And hence, in other words, the derivative of this free energy is only piecewise defined. You can only define it from here up to this point and from this point over to here, but at that point it does not exist. And because it does not exist at that point, that leads to this discontinuity in the energy. Okay, so now the next example we talked about was the magnetization. And by the way, that kink and the resulting discontinuity in the derivative, that is what I mean by pathological behavior. So mathematically pathological behavior means that at some points or regions, things behave weird, all right? So here, for example, at that point, the derivative is not defined, and that leads to a discontinuity. So that's what's meant by pathological behavior. All right, so now what we showed for the magnetization is that when you plot the magnetization as a function of temperature, what you get is a function that looks like this. So the magnetization decreases as you heat the thing up, and the thermal fluctuations overwhelm the spin-spin interactions until some point where the magnetization hits zero at the Curie temperature. And beyond the Curie temperature, you have zero magnetization. All right, so now, as we showed when we talked about the, what was it, the zero interaction model, that the magnetization is proportional to the energy, okay, which is again equal to the expectation value of the Hamiltonian. Okay, and now this, as we showed previously, this is already the first derivative of something that looks like the free energy. Okay, so here the magnetization is already related to the first derivative of the free energy, but we do not have a discontinuity. It is in this function, in fact, where you see this kink at this point. So at the critical temperature, you get a kink in the magnetization function. And what that means is that the next derivative of this thing, so if we take the derivative of the magnetization with respect to temperature, then or with respect to temperature, then you will get something that has a discontinuity. Okay, so this is, well, let me not write it as t, because we took the derivative with respect to beta for this first thing. Let me also say that this is with respect to beta, because they're the same thing, right? The beta and the temperature, they're the same thing, more or less. And so now what this means is that what we're doing is we're going to have a discontinuity in the second derivative of the free energy, like this. Okay, so in other words, it is a discontinuity in the second order derivative of the free energy. And hence, this is what's referred to as a second order phase transition. Okay, and in fact, if you go back and you look through your notes, what this quantity here is related to, the derivative of the magnetization, this is related to the susceptibility. All right, so this is also a general characteristic of second order phase transitions, is that there is some susceptibility involved. All right, so here it's a magnetic susceptibility, and what you get is a discontinuity in that susceptibility. Okay, so you get discontinuities and susceptibility. Oh, or I think I think this also shows up. Susceptibility is also something like, if I remember correctly, like a heat capacity. All right, so if discontinuities and susceptibilities or heat capacities, those are related to second order phase transitions. All right, so now we know a little bit about phase transitions, but now the problem is, even though we know a little bit about phase transitions, the Ising model, as we talked about it, doesn't have any damn phase transitions. Okay, so now our problem is that the first, or 1D Ising model, as we work through it, was, so one of the reasons we worked through it is that it is analytically pleasant, right? I mean, we were able to do nice math on it and get lovely closed form expressions for magnetization and free energy and so forth. So that's what, so its pleasantness is what made it analytically tractable. However, it's that same pleasantness which yields a free energy that does not have any pathological behavior, okay? So the 1D Ising model, there are no phase transitions, essentially because it is so nice and neat and clean and analytically tractable. Okay, so now to see phase transitions in the Ising model, you have to go to 2 or more dimensions. Now, the problem is once you go to 2 or more dimensions, it is no longer analytically nice, right? It becomes a real headache. It becomes so difficult that when you solve it, you get a Nobel Prize, right? Just like Professor Onsager. Okay, so what I want to do is to show you a model which it's not the full 2-dimensional model of the Ising model, because again, it becomes so analytically nasty that we don't want to get into it, but which at least captures some degree of this pathological behavior such that we can see that under some circumstances there will be phase transitions. All right, so let's do that, shall we? So let me get to my notes. Here it is. All right, so what we are going to do is something referred to as mean field theory for Ising model in 2+ dimensions. All right, and it's turns. I mean, this is good. It's super easy to understand. All right, so it's kind of remarkable how simple this is, and yet it still shows complex behavior like phase transitions. So let's talk about it. All right, so first of all, let's imagine what the Ising model looks like in 2 dimensions. All right, so for example, in 2D, you can have all, now the complication, and one of the things that makes this problem so hard is that when you make the transition from 1 dimension to 2 dimensions, the kinds of lattices that you can have blows up in your face, right? I mean, in 1 dimension, a 1-dimensional lattice is just, a bunch of dots. Okay, but then when you make the jump to 2 dimensions, you can arrange your dots in a whole bunch of different ways in 2 dimensions to yield a crystalline lattice. So for example, you could do something like have them all arranged in hexagons, or have them all arranged in triangles, or have them all arranged in, I don't know, Penrose tiles or some other crazy crap, all right? So essentially the level of generality goes through the roof once you make the transition to 2 dimensions. Okay, so what we're going to do in 2 dimensions, just to have a firm picture of the kind of thing that we're talking about, is we're going to focus on, well, just as an example, look at one kind of lattice. So let's look at a 2-dimensional, in 2D, let's look at what's called a cubic lattice. Okay, so a cubic lattice is exactly what it sounds like. I mean, it's a lattice that's made out of cubes. So now a cube in 2 dimensions is just a square. A cube in 3 dimensions is a cube. A cube in 4 dimensions is a hypercube, so on and so forth. Okay, so a 2-dimensional cubic lattice is just a grid of squares like this. All right, so there it is. And then we're going to put electrons at every node in this lattice. And again, associate with each of these electrons a spin and therefore a magnetic moment. All right, so now, this is like a two-dimensional generalization of our previous one-dimensional lattice, which looked like this. So equals here is probably not the appropriate symbol to use. Let's do what symbol? Let's use a squiggly line. So there, this is, if you just make one of the simplest possible transitions from one dimension to two dimension, you get this nice cubic lattice. But again, it's not the only possibility. You can have hexagonal lattice, triangular lattice, Penrose tiling, whatever you can come up with. All right, so now when we looked in one dimension, what we did was when we looked at a given spin, so let's say we look at this guy and call this the ith spin. When we summed over all the possible interactions, what we did was to only consider nearest neighbor interactions. All right, so in the 1D model, the nearest interactions are the interactions between that middle spin and the two guys on either side of it. Okay, so now when we make this transition to 2D, you can see that what you mean by a nearest neighbor kind of expands your mind, man, right? So for example, if we focus on, let's say, this spin, and we call this the ith spin, and we want to look at all the nearest neighbors of that ith spin, the nearest neighbors are these four guys, the ones that are directly connected to it by edges in your lattice. So now we have four nearest neighbors. Okay, and you can imagine, let's say, again, let's imagine, for example, a triangular lattice. So if we had a triangular lattice, oh boy, I'm really testing my spontaneous drawing skills here. So this is, for example, what a triangular lattice looked like. Or maybe that's a hexagonal, I don't know. Okay, so let's say that's our spin we're looking at. So you can see that what's called a nearest neighbor in this model would be different. In this hexagonal or triangular lattice, you would have, what is that, 6 nearest neighbors. So the number of nearest neighbors you have to worry about depends upon the type of lattice that you have defined for yourself in 2 dimensions. All right, does that make sense? Okay, so now if we are interested in nearest neighbor interactions, okay, so nearest neighbor interactions, essentially, the simplest thing we need to know ahead of time is how many nearest neighbors are we talking about? All right, and so the number of nearest neighbors you're talking about for a given lattice is what we're going to call Z. Okay, so Z is the number of nearest neighbors. And its fancy name is what's referred to as the coordination number. Okay, so the coordination number for a cubic lattice or a square lattice is 4. The coordination number for whatever the hell this thing is that I just drew, if this is triangular or hexagonal, or maybe it's both, I don't know what the technical term of this is, but you can see that this coordination number is 6. And hence what the coordination number is depends upon the lattice that you're working with. In general, for a cubic lattice, the coordination number is equal to 2 times the number of dimensions that you have. All right, so for example, in 1 dimension, okay, D is equal to 1, so the number of nearest neighbors you have, you can see, is 2. Okay, in 2 dimensions, D is equal to 2, so the number of nearest neighbors you have, you can see, is 4. And then if you were in 3 dimensions, what you would have, let's see if I can do this. you would have another dimension coming out and going into the page like this, where there would be another spin behind the page and another one in front, and you would have 6 nearest neighbors you'd have to worry about. Okay, so in general, for a cubic lattice, the coordination number is twice the number of dimensions that you have. We're actually not going to use that result. I just thought I'd tell you that for your own self-edification. All right, so now let's try to do something useful, shall we? So let's write down some mathematics. And again, in StatMech, generally the function that you're pretty interested in is the Hamiltonian. All right, so the Hamiltonian here is, it's, the general form is exactly the same as what we've been working through this whole time. It is equal to minus j times the sum over nearest neighbors of sigma I, sigma j, minus, now before when I wrote this, I would call this mu times the external field times the sum over each individual spin. So that's the spin interaction with the external magnetic field, just in order to keep the math nice and clean and make things easier to write. I'm going to replace mu b with h. Okay, so h is the external magnetic field times the dipole moment of your electron, or of your spin. Okay, so now, that's completely unchanged from what we've worked through previously. The only difference is when you perform this sum over nearest neighbors, essentially, how are you going to perform that sum depends upon the number of dimensions you have, the shape of your lattice, the number of your coordination number of your lattice. All right, so this sum and how you perform that sum is where the extra complication comes in. All right, so now, again, in general, in 2 dimensions, this turns into a horrifying mess. All right, but now what we're going to do is we're going to start making some clever modifications. Well, not even modifications, just some clever identifications. All right. So the first thing to notice is that what we have here for our Hamiltonian is 2 terms, right? We got this spin-spin interaction term, and we've got this spin external magnetic field interaction term. And they both have sigma I in it, right? So what I can do is essentially factor out the sigma I from both of these terms and write it in the following fashion. So I would write this as the sum over the ith spin of sigma I times minus j times the sum over sigma j. And this sum over sigma j is, again, just summing over, the j nearest neighbors of the ith spin. And my second term here is just minus h. All right, so now written like this, okay, the way that you should think about this is, again, what you do is first you pick your ith spin. So you pick one spin that you're talking about, okay, and then what you do is you come in here and then you sum over all nearest neighbors, and you think about how the external field interacts with that spin. All right, so in other words, this first sum is essentially iterating over every vertex in your lattice. And then once you go to that vertex, the first term is you just add up all the spins around that vertex, and then you think about how the external field interacts with it. All right, so for the cubic lattice, for example, the ith spin would be, say, this guy here in the middle. There we go. Okay, and then so this first sum is just picking, which spin goes in the middle. And then what the second sum does is it just looks at all the nearest neighbors. Okay, so this is sigma j, say, equals 1, sigma j equals 2, sigma j equals 3, sigma j equals 4. And it just goes around the lattice and sums up all the interactions from each of the individual neighbors. Right? I think that's pretty nice way to think about it. Okay. so now the thing to note, so what's going to happen? So what you're doing when you perform this sum over nearest neighbors is you look to see, okay, for this first nearest neighbor, what is its magnetic dipole moment? And as a consequence of that magnetic dipole moment, what is the field that that dipole moment is generating at the site of the ith spin? Okay, and then you go to the next one, and this guy's got some other magnetic dipole moment, and that's, you know, another magnetic field, and you say, what is the interaction of that magnetic field at the ith site? And so what you're doing is you're just going around and looking at what are the magnetic fields coming off of each one of my neighbors, and how does that influence the ith spin at the center of this group. All right, so another way to think about this is that, okay, so let's think about this. So in other words, I'm summing over nearest neighbors of the jth spin like this in this first term. Now, if so I'm just essentially summing up all the magnetic fields. It's just superposition of magnetic fields. If I take this number and I divide it by the coordination number, okay, then what this gives me is essentially the average magnetic field at the ith site. Okay, so let me call that average of mi. Okay, so in other words, I'm just adding up all the fields from the neighboring spins, and then if I divide by the number of neighboring spins, that tells me what the average field is at that location. Does that make sense? Okay, so this is the average magnetic field from nearest, that's not how you spell nearest, you dope, nearest neighbor spins. Okay, like that. And just to keep the math looking clean, I'm going to get rid of that. So I'm just going to call it average M, okay? So with that identification, we can write our Hamiltonian in the following way. It's the sum over ith spins, okay, times minus J times the average field coming from my neighbor spins. And then you can see, so this thing is what is in my original Hamiltonian right here, right? So you can see that what I have to do is, let me just say it, that the average of M times the coordination number is equal to this, All right, so when I write out my Hamiltonian, I'm going to replace the sum with the coordination number times the local field. So it's just JZ average field. Okay, and then we've still got our interaction with the external field, like so. Okay, so now, so far, I haven't made any kinds of approximations, right? All I've done is this is just exactly the same original, exactly correct Hamiltonian, written just in a different way. All right, so now is when I make an approximation. So now I'm going to make what's called the mean field approximation. All right, so the mean field, so the mean field approximation is very simple. All right, so what we have in this term right here, again, this is like the mean field coming from all the neighboring spins at each individual lattice position in the lattice. All right, so that makes sense, right? Okay, so now what the mean field approximation is simply that there is nothing special about any individual vertex in the lattice. That, you know, in principle, each of these numbers at each vertex in the lattice can be different, right? So, I mean, depending upon the orientation of the neighbors in your lattice, you could get some different value for this local magnetic field at every point in the lattice. So what the mean field approximation assumes or approximates this as is saying that there's nothing special about any individual lattice there's any individual vertex in the lattice, and you essentially just treat them all the same. Okay, in other words, this local magnetic field at each individual vertex, we're going to say is equal to just the total magnetization of the material. Okay, so in other words, you're essentially averaging over every vertex in the lattice, okay, and saying that they all, to first approximation, are experiencing the same local field from spin-spin interactions. Hence the name mean field. You're just taking like the average and saying they're all the same. Okay, does that make sense? Okay, so where this is capital M, this is the magnetization. All right, so the mean field approximation is where you take this local nearest neighbor field and replace it with the overall mean magnetization of the entire material. Okay, so the mean field approximation is when you go from this to this. I just replace the average local field with the net magnetization. That's it. Okay, that makes sense? All right, so now you can see what this has done is, the reason this Hamiltonian here is so painful to calculate exactly is precisely because of the nature of how on earth do you take this sum over nearest neighbors. And how you take that sum depends upon a whole bunch of things. How many nearest neighbors you have, what's the shape of the lattice, da-da-da-da-da-da. And so now what we've done with the mean field approximation is to replace that complicated, nasty sum with just a single number, the magnetization. And now this thing is, it's not so bad looking anymore, right? We can do this. Okay. And again, I emphasize, so what we're doing here again is summing over each side in the lattice. And each side in the lattice, again, can only either be up or down, right? So this sum is going to be really nice and simple to calculate. So for example, if we were to calculate the partition function of this, given our mean field Hamiltonian here, what this is again, the sum over all possible values of sigma I of e to the minus beta h, okay, where h is this now mean field Hamiltonian. And you can see, so I got a minus sign here, I got two minus signs here. I'm just going to, goodbye minus signs. And I'm left with this, J, Z, M, I believe, so I have in my notes minus H, but I believe that should be plus H, you silly monkey. All right, so there it is. So that's our partition function. And now, that's super easy to calculate, right? Because sigma I can only either be plus or minus 1. So now all we got to do is just plug in sigma I is plus or minus 1. And when we do that, we get e to the beta j z m plus h plus e to the minus beta j z m plus h. Oh ho 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 ho! I'm having flashbacks now. Yes, this looks very familiar to things that we've done previously, does it not? And there's probably some, there's probably a power of in there somewhere for however many lattice sites that we have. Who cares about that, right? So again, what this thing comes out to be is just 2 times the hyperbolic cosine of j z m plus h. All right. Oh, I'm sorry, I forgot a beta, and that beta is actually very important. So there's a beta J, Z, M plus H. There it is. So that's our partition function. And again, there's probably powers of n in here if you want to be rigorously correct, but that's not going to do anything interesting. So we're just not going to worry about it. All right. Okay, so that is our partition function. All right, and so now we're gods, right? We have the partition function. We can figure out exactly how this system behaves. In particular, what we're interested in is the magnetization, right? We're interested in how this thing acts as a magnet. So the magnetization is equal to the negative derivative of the free energy with respect to H. For reasons that we've talked about many times in previous lectures. All right, so you just, you take this thing, you take the logarithm, and then you take the derivative of that logarithm with respect to H, and that will give you the magnetization. And it's going to look extremely similar to the magnetization that we got previously, right? Because when we talked about the 1D Ising model, our partition function, again, it looked like this hyperbolic cosine. So, I mean, this is going to look exactly the same. When we take the derivative of this thing, what we're going to get is a hyperbolic tangent. So it's tanh beta J Z M minus H. Okay, so now let me write this like this. Magnetization is equal to tanh beta J Z M minus H. So that's our answer right there. There it is. And you say, Professor Kuhlman, this is exactly the same answer we got previously. This is not interesting. And I say to you, my young Padawan, that is not necessarily correct, because what we had previously was that the magnetization was equal to the hyperbolic tangent of, so let me see if I can remember what they are. So for the no interaction, so 1D no interaction, we had that the magnetization was at least proportional to tanh beta, what we would call here H, right? So that was our magnetization for no interaction. For the 1D no field, no external field, we had that the magnetization was proportional to tanh beta J. All right, so these are very simple, right? Because what you're interested in plotting here is the magnetization as a function of either T or H or J or whatever, okay? And that's very easy to do because you can just see you have magnetization as a function of your X variable. This thing is not that simple, you see. All right, so what makes this more complicated is that you can see that this is actually a transcendental equation, right? Then we have an expression for the magnetization in terms of some complex function of the magnetization, right? So in other words, it's like duck season, wabbit season, right? I got an expression for one thing in terms of itself. Okay, so this thing is quite a bit more complicated. And as I said, it's transcendental. You can't get a nice, clean, analytic expression for the magnetization from this. All right, so how do we get from this expression how the magnetization behaves? And what we're going to do is to take some lessons from nonlinear dynamics. All right, so let me take that equation and rewrite it like this. I get the magnetization. In fact, let me use different colors even at this level. I have the magnetization minus, use purple, the hyperbolic tangent of some function of the magnetization plus H. And this is now going to be equal to 0. I mean, that's just, I've rewritten, and I'm sorry, this should be a plus sign, not a minus sign. So all I've done is just taken, everything and move it over to the left side of the equation. And so now the way to see how this thing behaves is graphically. All right, so what I have here is two functions, right? I have this function, M, and I have this function, tanh of M, and what I'm interested in is where those two functions are equal to one another. All right, so what I'm going to do is to draw both of these functions and see where they cross each other, and where they cross each other are the solutions to our problem. All right, but now before I do that, let's remind ourselves what this tanh looks like. Okay, so previously, so again, let's go back to this guy. It's 1D, no interaction thing. So for the 1D, no interaction Ising model, we had the magnetization was proportional to tanh beta H. And when I drew this thing, what I showed you this looked like was the following. Had some maximum value, had some minimum value, and then it looked like this. Okay, so that's a that's a hyperbolic tangent. And now what I told you is that this region where the thing smoothly transitions from one magnetization to the other, the width of this region depends upon the temperature. That depends upon beta. So the lower the temperature, the sharper this thing is going to be. That is essentially the less contribution thermal fluctuations have to its appearance. The higher the temperature, the more spread out it's going to be. All right, so in other words, this tanh is a function of beta, both here and in our current mean field problem. And so the temperature is going to affect what the shape of this tanh function looks like. And so what I need to do is to draw it for different temperatures. So for low temperatures, it's going to be nice and sharp. For high temperatures, it's going to be nice and smooth. All right, so let's try that. Okay, so we have, again, do different colors just to make things super, super obvious. Tanh beta JZM plus H minus equals 0. So again, what I'm going to do is I'm going to plot this function and this function, and where they cross, those are our solutions. All right, so first of all, let me do it for low temperature. So for low temperature, so on this axis, I'm going to put the magnetization, and then here I'm going to plot, whatever my function looks like. All right, so at low temperature, this tanh function is very sharp. So it's going to look something like this. All right, so that's tanh at low temperature. Now, the magnetization. So now when I plot this function, what this function is that I'm plotting here, I'm going to plot y is equal to m. In other words, I'm plotting m versus m. In other words, it should just be a straight line, right? So it should just be a straight line with slope 1. So that's going to look something like this. There it is. Okay, and so now what we're interested in, the solutions of this equation are when these two functions cross. And you can see that there are 3 points where it crosses. All right, so now this is boring, right? This is 0 magnetization. That's what we got previously at no external. So now again, we plot it without any external field, and you still get tanh JZM. So tanh JZM, this is what we got previously. That was our solution previously, is that there was no magnetization. Our new solutions out here, these are the interesting ones. These are non-zero magnetizations, right? And it'll be the same value, either plus or minus, just depending on what you define as plus or minus. All right, so by looking at this more complicated model that generates this transcendental magnetization function, you get these non-zero spontaneous magnetizations with no external field. All right, now let's look at what it looks like at high temperature. Okay, so again, I plot magnetization and F of X. F of M, actually, I guess is what it should be. M. Okay, so now, again, our magnetization is just, or this first function is just a line with slope 1. And as the temperature gets higher, the tangent is going to get smoother and smoother. So it's going to start to look something like this at really high temperature. Oh, shit. Excuse my language. So that's high temperature tangent. And you can see that at high temperature, it only crosses at 1 point, 0. Okay. And so this only, you only have a solution at high temperature when there is 0 magnetization. Okay, which, you know, that's exactly what, where is it? This function we drew right here looks like. So at low temperature, you have a non-zero magnetization. You crank the temperature up to some critical temperature, and then the only solution is 0 spontaneous magnetization. All right, so that's what's happening here. Is as you increase the temperature, the tangent gets flatter and flatter, and at some point you only get one solution. Okay, so for T less than the critical temperature, you get 3 possible solutions. One of which is no magnetization, and the other 2 are non-zero spontaneous magnetization. Once you cross the critical temperature, then there's only one possible solution, which is no magnetization. And so now you can see there is a special, as you increase the temperature and this thing gets smoother and smoother, there's going to be, you know, one specific temperature where this line is exactly equal to the tangent of this hyperbolic tangent curve. And so that's going to be the point where it makes the transition from 3 solutions to 1 solution. And so that point where M, where M is tangent, exactly tangent to tanh beta JZM at M equals 0, that is the critical temperature. Okay, so that's easy to do. We just say, you know, the slope of M at M equals 0 is equal to the slope of this tanh function. Oops. At M equals 0, and then we just take these derivatives and find the temperature at which this is true. All right, so what we get is 1 is equal to 1 minus tanh squared beta Z, and this is at the critical temperature, ZJM times beta CJZ at M equals 0, and then you just solve for T. And what you get is that the critical temperature is J times the coordination number divided by Boltzmann's constant. There, you've done it. So what we've shown is that by getting this more complicated free energy, essentially, that relates a function back to itself, such that you have this transcendental relationship, you get a solution that makes this transition from multiple possible solutions to just a single possible solution at some critical temperature. It's a phase change. Ta-da. All right, so we're done. And we're actually out of time. So that actually went a lot better than I thought I was going to be done in like 15 minutes. But luckily, I can talk a lot about not so much. All right, so any questions about anything? All right, very good. So then I hope you all had a pleasant enough time in this class, notwithstanding all the external weirdness. Don't forget to turn in your homework on Friday. Don't forget to turn in your final next Thursday. And people are saying things in the chat. thanks for teaching us stuff. I hope I, in fact, did teach you something. And I'll see you guys later. All right. Toodaloo.